whatever the steel required for the whatever the shear load which has been remaining after the removing the concrete, whatever it has been taking for the steel, how much shear force is induced, that we have calculated. That was Vu minus Vuc. Okay, so according to this, the Vus, the value we have calculated, it was 85.55 kilonewtons. Okay, so now we are to calculate the spacing of the bars. So shear stress, shear reinforcement, we are going to provide 8 mm 5 four-legged stirrups we are going to provide. So for that, in the IS 456 page number 73, in that clause number 40.4.a, clause number 40.4.a, in that for vertical stirrups, the formula has been given. Just check out that formula, page number 73. For VUS, the formula has been given. Viresh, are you there?
Yes, sir.
What is the formula
Yes,
for
sir.
vertical stirrups?
VUS is equal to 0.87 FY ASV D by SV.
Okay. So this is the formula we'll be using from the clause number 40.4.8. So according to that, the value of VUS is equals to 0.87 FY ASV D in divided by SV. Okay. So the value of VUS is known to us. What is the steel we are going to provide? What was the FY? Which steel we are providing here? Which grade of steel?
415.
415 we are using. Then ASV is nothing but it is the spacing. It is the area of shear reinforcement. So area of shear reinforcement, it is 8 mm 5 four-legged. Okay. So 4 into pi by 4 into d square. Into d is nothing but it is the depth, the effective depth of the hill. Then SV is the spacing. Okay, out of that SV, only the spacing is unknown to us. VUS we have calculated here 85.55 kilonewtons. So just I will replace the values. VUS will be in the denominator and SV will be on the other side. So according to this formula, so pi by 4 into 4 numbers will be there. So I have taken only pi. The depth of effective depth of hill, it is 275, and VUS is 85.55 into 10 raised to 3, that is kilonewton. I have converted into newtons. Just tell me what is the spacing of bars, spacing of stirrups. Calculate the spacing of stirrups.
233.35.
Ashraf Ali.
Yes, sir.
Calculate and tell me what is the spacing. Calculate the spacing, Ashraf.
Two 233.35, sir.
233.35. Yes, it is 233.35. So hence we will provide the spacing as 225 mm center to center of 8 mm 5 four-legged stirrups. Okay, so here we complete the design of heel portion. Now let us design for the toe. Okay, so for that we have to go for the calculation of loads and movements. Okay, so whatever they are acting, on the toe. So the dead load of toe, then the earth load in the foundation, which will be acting in the downward direction, these two forces, and upward, that is the upward soil pressure that will be acting. One is the rectangle portion, another one is the triangular portion. So somewhere here we have drawn the pressure distribution diagram. Here it is the pressure distribution diagram. So this phase we have to consider this area for the calculation. Okay. So before that, the dead load of this particular portion, that is the heel portion, toe portion, we have to consider. So what is this length?
1 meter.
1 meter. And depth of this, overall depth of toe, whatever we have provided,
0.315.
0.315. Okay, so the dead load of this one, it will be equal to 0.315 into 1 into the density of concrete, RCC, density of RCC. What is the density of RCC? 25. Just calculate and tell me what is the load.
7.87.
7.87. Where it will be acting from this portion, this face? From this face, where it will be acting?
Center.
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 Means what will be the distance from here to here?
1/2.
1/2, that is 0.5. Okay. So calculate the movement also. 0.5 into your whatever the dead load you have obtained.
3.935.
3.935. Okay, so there is a soil pressure also above this particular portion of the toe. So for that also we have to calculate. So the length will be 1 meter. Again, the length will be 1 meter. What is the depth of this portion of soil? Soil above this, what is the depth? From ground level to the top of the toe.
0.985.
0.985. 0.985 into 1 into what is the density of soil? Density of soil?
18.
18 kilonewtons per meter cube. Okay. So again, it will be acting where? From here to somewhere here. What will be the distance from this face where it will be acting? Point 985 into 1 into 18 is the density. That will be your load. So what is the load?
17.73.
17.73.
17.03. So where it will be acting from here, from this face?
1/2.
1/2 again. Okay, calculate the movement also.
8.865.
8.865.
Okay, so it is 7.87 for the dead load of toe portion multiplied by 0.5, so it is 3.93. Then the earth load in the foundation, it was 17.73 acting at 0.5, so 8.86. Okay, so these are the downward forces. Upward forces, we have to calculate the area of the trapezoidal. I will divide the trapezoid into two parts. One, that is the rectangle GFIJ. So for this portion, this length is equals to 1 meter. We know this length is 1 meter. So 1 meter into this distance I want, G to J. G to J I want the distance. If the pressure at I is equals to 100.06, what will be this distance? Up to here. G to J. What is the distance GJ?
100.06.
100.06. So 1 into 100.06, again 100.06. Okay, so where it will be acting from this face?
0.5.
0.5. Okay, then we will calculate the area of this triangular portion, that is IJH. IJH, for this portion I want to calculate. This length is 1 meter. This length is IJ is 1 meter, and JH we have to calculate the distance JH. Okay, the pressure at H is equals to 170.13, and the pressure at J is 100.06. So what will be this distance JH?
Seventy point zero seven.
70.07.
70.07. Where it will be acting from this face now?
2 by 3 of 1.
2 by 3 of this 1 meter. 2 by 3 of this 1 meter. From here it will be acting at 2 by 3 of 1 meter. So it will be, I think, 0.66.
Yes, sir.
Let us see. 100.06 into 0.5. Just check it. 150.03.
Yes, sir.
And similarly here 34.76. That is 1/2 into 1 into 69 point, 70.07. 70.07. Just check it. 34 point something this value.
Thirty-five point zero three.
35.03. It will be acting at 0.66. So calculate the movement also.
$23.11.
23.9. Okay, so summation, add these forces with the sign conventions, as well as add these movements with sign conventions. So these two values are negative, these two values are negative, these two are positive, here these two are positive. Calculate the movement as well as summation of load.
Minus 60.68.
Load is equals to
Moment
Load
equal to
110 load.
110. Okay, and movement
60.68.
60.68.
61.41.
60 point
61.41.
61.41. Okay, so these are the values 61.41, and here 110 point something. This is the load. Okay, so now let us check for the depth of whatever we have provided, depth of toe, so whether it is safe or not. So for that, D required, calculation of D required we have to do. So here M equal to 61.4 kilonewtons meter. So movement is this much. Factor this movement by multiplying 1.5. What is the value of mu?
92.1.
92.1.
92.1. So now let us equate mu with mu limit for Fe5 and 415 steel. What is the value of mu limit? For Fe415, what is the mu limit?
0.138 FCK BD square.
0.138 FCK BD square. So the same values I have taken, 0.138 FCK BD square. So FCK is 20 concrete grade we have given, it is 20. So for 1000 meter, 1000 mm, that is 1 meter we are calculating. So this is the D, this is the mu, whatever we have calculated. So I think it is 92 point something, no?
92.1.
92.1.
92.1 into 10 raised to 6, 0.138 into 20 into 1000. Just calculate what is the value of D required.
182.67.
182.67.
182.67. So 182.67, it is less than whatever we have provided. So hence it is okay. We have provided D equal to 275 mm. Okay, that is the effective depth we have provided 275 mm. So now let us go for the calculation of main steel. So we know the formula for the main steel. AST into AST equal to 0.5 FCK divided by FY. 1 minus root of 1 minus 4.6 mu divided by FCK BD square into BD. So replace these all the values. Here it will be I think 92 point something. Remaining other values are correct one. So just calculate what is AST.
Thousand 4.14.
Arcia, what is AST?
1002.14.
1002.14. Any other has got different answer? Anybody have got different answer?
1003.1.
1002.14.
Yes, sir. 1003.1, sir.
Okay. So just we'll provide 16 mm 5 bars. 16 mm 5 bars. So let us see what is the spacing for this 16 mm 5 bar with the AST, whatever it is calculated. 1003 point or 1002 point something, that value we have calculated. Just check what is the spacing you opted.
200.23.
200.44, sir.
200.44.
200.44. Okay. So we'll provide the distribution steel as 16 mm 5 bars, 200 mm center to center. Less than that, whatever required is there, less than that, but round figure. So it is 16 mm 5 bars at 200 mm center to center as distribution steel. Okay. So next one will go for the calculation of distribution steel. So distribution steel, we know that how to calculate it. 0.12% of Ag, that is the gross area. So it is 0.12 divided by 100 into 1000 into gross area. It is 315 is the depth. Okay, just calculate what is the ASTD.
378, sir.
It is
378.
378.
28. So again, if I provide 10 mm 5 bars, what will be the spacing here?
Two 207.77.
207.7.
207.7.
207.7. Okay, so 207.7 mm. So let us provide 10 mm 5 bars at 200 mm center to center as distribution steel. Okay, so this is the calculation of distribution steel. Now let us go for the check for shear. So shear force, I think 110 point something it was there. We have calculated earlier, somewhere here. The force, total force, we have calculated here. So it is 109.75. So factor it. So VU is equals to V into 1.5. So it is 110 point something into 1.5. So tell me what is the value of VU, shear force, factor shear force.
165.0.
165.7.
165.7. Okay. Calculate tau V with the values. VU we are knowing 165 point something into 10 raised to 3 divided by B is 1000 and D is 275.
0.6.
0.6, sir.
0.6. Okay, so it is 0.6. Then let us calculate what is the percentage of steel. So percentage of steel provided. So pi by 4 into D square. So main steel I think 16 mm 5 bars we have provided into 1000 divided by spacing was 200 into 100 divided by 1000 into 275. So percentage of steel provided
0.36%.
0.365.
0.365. So it is 0.36. Okay. So now from table number 19, IS 456 for 0.36 for 0.36 and M20 concrete, what is the value of tau C? It will be in between of
0.25 and 5.
0.25 and 0.5. Okay. So for M20 concrete, for it is percentage of steel 0.25, it is 0.36 tau C, and for 0.5 it is 0.48, 0.36 and 0.48. Just check it out whether the values are correct. For 25, 0.25, 0.36 and 0.5, it is 0.48. Is it correct? Then go for the interpolation method. So 0.5 minus 0.25, it is 0.25, 0.36 minus 0.25, 0.11, then 0.48 minus 0.36, 0.12, and x minus 0.36. Go for the calculation cross multiplication.
0.4128.
0.4128. So it is 0.4128 newtons per mm square. So it is less than tau v. Okay, so it is again less than tau v. So tau v it is I think 0.6, isn't it? 0.6.
Yes, sir.
Yes,
So
sir.
whether I can I say it is safe against shear?
Yes, sir.
Is it safe against shear?
No, sir.
No, it is not safe against shear because tau v should always be less than tau c. So in our case, tau v is greater than tau c. Okay, so due to that reason, it is not safe against shear. Okay, so for that we have to go for the shear reinforcement. We have to calculate the shear reinforcement for vertical stirrups. For vertical stirrups, VUC, that is shear force resisted by concrete, we will be calculating, that is tau c into BD. So tau c we have calculated here 0.41 into 1000 into 250. So tell me what is VUC?
One hundred 12.7 to 10 raised to 3.
112.75
75 into 10 raised to 3.
112.7.
112.75 kilonewtons. Okay, so now we will calculate VUS. So how to calculate VUS now here? How we will be calculating VUS?
VU minus VUC.
VU minus VUC. So VU minus VUC will do. So what is the value of VUS now? VU 165 point something, and this I think it is 112.75, na?
Yes, sir.
Tell me what is VUS?
52.95.
55.55.
50,
52.55.
55.51. Okay, so for this we have to design the shear reinforcement. Let us provide 8 mm 5, but here now will the force is less as compared to earlier whatever force we have calculated here in the hill part. So we will provide only 2-legged stirrups, not 4-legged stirrups, because the load is less than earlier whatever we have calculated. So let us provide 8 mm 5 2-legged stirrups. So again from the IS 456 clause number 40.4.8, we are having the formula. So it was VUS equal to 0.87 FY ASVD divided by SV. Okay. So from this clause, the formula is there. So the same formula we have taken. So VUS is known to us here. Then FY is known to us. ASV we have assumed 8 mm 5 bars, 2-legged. D, that is the depth, 275. SV we have to calculate. Okay. So tell me what is the value of SV. Spacing of 8 mm 5 2-legged stirrups.
One 90.88.
190.88. 190.88. So let us provide the stirrups at the spacing of 190 mm center to center. Okay. So less than the value whatever we have obtained, but in the round figure 190 mm center to center of 8 mm 5 2-legged stirrups. Okay. So here we complete the design of toe. Now let us go for the design of shear key. So we know that as our FOS, that is the factor of safety for the sliding, was less than 1.4. So we have to design a shear key. So let us design the shear key. So pressure at the face of toe will be equal to the pressure at face of shear key, the same pressure. So here in the pressure distribution diagram, this pressure, this, what is the pressure at this face? At this face, what is the pressure? For this face, what is the pressure? What is the pressure here?
100.06.
100.06 will be the pressure at this face. Okay, so the same pressure we have to consider here for the design. So 100.06, the same pressure we have taken. Then if A is the projection of the shear key, we have to calculate what is the distance of A. For that, resistance offered by the passive work pressure we have to calculate. So we have been given with the Ka, that is the active soil pressure. So we have calculated it, 1 minus sine phi divided by 1 plus sine phi, that was 0.33. So the passive work pressure Kp, the value of Kp will work out about 3. That is 1 divided by 0.33. So it is 3. Okay, so coefficient of earth pressure Then factor of safety, again sliding, we know the factor of safety should not be greater than, it should not be less than 1.4. So for that, 0.9 into summation of load into mu plus kp into 100.06 into A divided by horizontal thrust, that is P. Okay, so these are the downward loads, this is the upward load. Okay, pressure, sorry, this is the downward load, this is the horizontal load, P is the horizontal load. We have calculated while the check for sliding. So at the initial part, check for sliding. So somewhere here for this portion, here we have calculated the load. So it was 413.71. It should be multiplied by 0.9 and mu is 0.5 and horizontal pressure is 137.33. Okay, so from this we have to subtract the horizontal pressure at the face. So load due to the pressure of the face that we have calculated here, it is 100.06. A has to be calculated. So just calculate, if the factor of safety is 1.4, the only unknown is A. Just calculate the value of A. A will be equal to what? What is the value of A? What is the value of A?
Zero point zero.
0.02.
0.020.
So required depth of shear key with all the forces, whatever they have been acting over this retaining wall. So according to that, the required it is 0.02 meters. Okay. So hence we provide 100 mm, that is 0.1 meter as the depth of shear key. Okay. So depth of shear key 100 mm we will be providing. So the steam reinforcement will be continued for the shear key. So hence it is not required to design for the extra reinforcement for the shear key. The same, whatever the steam reinforcement is there, it will be continued for the shear key itself. Okay, so here we complete the design of shear key also. Okay, so any doubts here?
No, sir.
Any doubts? Anybody is having any doubts? Please let me know.